Hey guys, so today we're doing lesson 6.2, which is systems of equations with two variables continued, but now we are learning a new method or reviewing a new method really from Algebra 2, which is elimination method. Okay, so as normal, please go ahead and pause the video. You can work out the warm up on your own, and then we will go ahead and go over it. So number one is reviewing solving systems of equations by graphing, which is what we did in the previous lesson. So here I'm just going to put stars with different colors by these specific equations. My first one here has a y-intercept of 3, and then the slope is -2. If I write that as a fraction, that's -2 over 1. So I'm going to go down 2 over 1 to the right, down 2 over 1 to the right, etc. And remember that anytime you're graphing, you do want to fill up the entire coordinate grid. Okay, for the second equation, we have a slope of 1/2 and then a y-intercept at -2. So for the slope, I'm going to go up 1 over 2, up 1 over 2, and then backwards down 1 over 2 to the left. Go ahead and draw this. We want to label our lines unless you're color coordinating like me, and then we are looking for our point of intersection. So here they intersect at the point 2, -1, which would be our solution to the system. Okay, second problem here, we are solving the system of equations by the algebraic method of substitution. So first we look to see, do we have one of the equations already set equal to a variable, x or y, which yes, we do. The first one is set equal to y, so then I can take that expression that y is equal to and substitute it in for the y in the second equation. So I'm going to rewrite that over here, 4x plus 4 times, instead of y, we're going to plug in this value, -6x minus 4, and then all of that is equal to -16. So now we go ahead and solve for x. I'm going to distribute here and get -24x, -16. Okay, combine my x terms, so 4x minus 24x is -20x, minus 16 equals -16. I add the 16 to both sides. I get -20x equals 0, and then don't stop here. We still divide both sides by the -20. So x equals 0. That's our first variable. And then we plug that back in to one of the original equations. I just use whichever one looks easiest. So I'm going to use the top one because that is already solved for y, or y is already isolated. So y equals -6 times, plug in this value here for x, which is 0, all of that minus 4. So -6 times 0 is just 0, and 0 minus 4 is -4. So y equals -4. Okay, and then we can write our coordinate point, x comma y, so 0 comma -4 is our solution. All right, so elimination method, as a reminder, this is another algebraic method of solving systems of equations, and specifically today we are working with systems of equations with just two variables, x and y. Now, elimination is what it sounds like. This is when we get rid of or eliminate a specific variable, just like we do in substitution method. However, when I would say this is best is when you are using an example like this one down below here, where both of the variables are on one side of the equation. So notice both x and y are on the left side, both x and y are on the left side. That is usually when it's going to be easiest to use elimination method, because then you don't have to go through the process of rewriting to try to solve for x and y to then use substitution method. You could still do that technically, but this is just going to be a little bit of an easier setup. Okay, so how do we do elimination method? Well, we'll talk about that a little bit more in the examples, but we add the entire equations together. So basically it becomes one big addition problem to where, okay, I would add these, and if you notice here, I have a positive 2y and a negative 2y, and so if I add those, that y variable would very quickly eliminate, and then we'd be able to continue solving. Okay, so here are the steps for elimination method. Step number 1, you want to write the system so that the terms are aligned, just like we looked in the previous example. My x's were in the far left column, my y's were in the next column, the equal sign was aligned, and then we had our constants or our numbers here on the right side. Okay, so you want to write them so that the terms are aligned. Step number 2, you want to eliminate one of the variables and then solve for the other. So that's where the elimination method comes into play. Step number 3, we want to substitute whatever the first variable is, whatever that value we get is, into the other equation and then solve for the other variable. And then step number 4, we write the answers that we just got for our variables as a coordinate pair. Okay, so first example, we're going to do elimination method using basic addition. Okay, now I notice here, this is a good candidate for elimination method because like we talked about, both my variables x and y are on the same side of both equations. They are already aligned, so my x's are here, my y's are here, equal signs here, constant here. So I don't have to do that first step. Technically, it's already been done for me. So step number 2, I go ahead and I add these equations together if I see that one of the variables is going to easily eliminate, which it will because I have a negative 2y and a positive 2y. So you need to have opposite sign and the same number, same variable to then be able to cancel those out. Okay, so when I add this, I just add down x plus 5x is 6x, negative 2y plus 2y, that cancels or eliminates, that gives me 0, and then negative 19 plus 1, so make sure you're still adding on the outside of the other equal sign. Okay, so that gives us negative 18, my y's are eliminated, and then I continue solving for this variable by dividing by 6, and I get x equals negative 3. Now I need to take this value and plug it back in for one of the original equations. Again, does not matter which one. If you've solved this correctly, it will give you the same answer either way. So I'm just going to pick that first equation because I noticed that the numbers are a little bit smaller and easier to work with, at least on the left side. So I'm going to plug in negative 3 for x minus 2y equals negative 19. Okay, and then I'm going to go ahead and solve for my y value, so add 3 to both sides. I get negative 2y equals negative 16, divide by negative 2, and I get y equals 8. So my coordinate point, or my point of intersection, would be negative 3, comma 8. And again, you can always go back and double check that this works by plugging negative 3 in for every single x in the original equations, 8 in for every single y in the original equations, and seeing if you do in fact get the left side to match the right side. Okay, so an important thing to note is that, yes, oftentimes we can just add our two equations together and eliminate a variable. However, if you are trying to eliminate a term and they have the same sign, if you add them, they're obviously not going to eliminate. One has to be opposite sign. So instead of doing that, what you can do is you can subtract one of the equations from the other instead of adding. Or a simpler way to do this is just multiply one of the equations by a negative 1, or in some instances, you might need to multiply it by an actual constant other than 1 as well. Okay, so let's look at an example of this, which is technically elimination using subtraction. So I see my variables are on the left side of both equations, and I notice if I try to eliminate here, I have a positive 4y in the top equation and a positive 4y in the bottom equation. So those are going to be my easiest terms to eliminate. However, they're the same sign. So if I were to add 4y to 4y right now, I'd get 8y. Instead of doing that, like we just talked about, we would want to multiply one of the equations by a negative 1. It does not matter which one, so I'm just going to multiply the second equation by that. And then I'm going to rewrite what I have over here. So 3x plus 4y equals 18. That stays the exact same. And then when I multiply this negative 1, make sure you are distributing that to every single term, including this one on the other side of the equal sign. So all my signs flip. This becomes positive 2x, a minus 4y, and a minus 8 on the other side. And the reason that we like to do that instead of just writing a subtraction symbol out in front is so that you do not forget to switch every single sign. I think it just makes it a little bit easier to distribute it first, and then you can still add down, and then you're going to see, okay, now I have a positive 4y and a negative 4y, and that's going to eliminate. So when I add these, I get 5x equals 10, divide by 5, I get x equals 2. So that's my x value. and then I can go ahead and plug that into one of the original equations. I'm going to plug that into the top equation again, just because it doesn't have negatives. So 3 times my x value, which is 2, plus 4y equals 18. Now I can go ahead and solve for y. So 3 times 2 is 6. I can subtract that 6 from both sides. I get 4y equals 12. Divide both sides by 4, and I get y equals 3. Okay, so there is my solution, 2, 3. So again, the only difference here that we did with the original setup was we had to multiply one of the equations by a -1 first so that we would have our variables eliminate by being opposite signs. Okay, another example, this one's a little bit different because if you look here, unfortunately, you cannot simply add or subtract these equations and automatically eliminate one of the variables because we have a 2x and a -x. Okay, those are not the same term but opposite signs. One has 2, one just is a -1, and then this one is a y and a 3y. We need them to match, and so when this happens, we're going to have to multiply one or potentially both of the equations by another number to then get our x's or our y's to match. So it really doesn't matter which one you choose here. I just look at whichever one is going to be easiest or the smallest number. So I could get if I wanted to match the y's, this is a 3y, I could multiply the top equation by a -3 to make this a -3y, or if I want my x's to match, which is what I'm going to do today, this is a 2x. If I want this -x to become a -2x, I just multiply by 2. The reason I'm going to do that is because I'm just multiplying by 2. I don't have to change it to a negative sign or anything like that. So again here, make sure you distribute that to every single term. Okay, so I'm going to rewrite the top equation, that one staying the same, and then distribute this. I get -2x plus 6y equals -24. Now before you go ahead and add these, just double triple check that you are going to be able to eliminate, which yes, I am. I have 2x and a -2x. So when I add those eliminate. I get y plus 6y, so 7y, and then 3 plus -24, which is a -21. Then I divide both sides by the 7, and I get -3. Okay, so then I can take this, plug it back into one of the original equations. I'm going to use this top one because that looks a little bit easier. So 2x plus, plug in our value that we just found for y, which is -3. All of that equals 3. So plus a -3, that's the same thing as just -3. If it helps you to rewrite it, you can, or you can just automatically add 3 to both sides. Up to you. We get 2x equals 6, divide both sides by 2, and then our final answer is x equals 3. Okay, so my coordinate point here is 3, -3. Now be careful here, even I am guilty of this sometimes. We solved for y first, but I need to make sure that I put that as the second value in my coordinate point because x, which comes first in a coordinate point, is 3. Okay, let's do one more example using multiplication first, and then we'll do an application problem. So let's take a look here. We've got a 2x and a -3y, and a 5y and a -4y. So first I see, okay, can I get from the smaller value to the larger to get my variables to match? So could I get from 2x to -3x by multiplying by a whole number? Nope, I could not. I could multiply by decimal, but that's just going to make all of our numbers a little bit messier, so I'm going to try to avoid that. And then I look at the y's. Could I get from a -4y to a 5 by multiplying by a whole number? I could not do that as well. So in this case, I'm going to have to multiply both equations by a number to get my variables to match, or one set of them. So I'm going to just pick the lower numbers, 2 and 3 versus 5 and 4. And in order to get to a common number, I can just multiply by the opposite number. Okay, so if I want 2 and 3 to get to a number that they're going to match with, I would choose 2 times 3, which is going to be 6. So the top equation, I would multiply by 3, and then the bottom equation, I would multiply by 2. The reason I don't have to multiply because they are already opposite signs. The positive is in the top equation, and then the negative is in the bottom. So I can simply multiply those both. And again, make sure you distribute to every single term. So I get a 6x plus 15y, and then 26 times 3 is 78. The bottom equation is going to become a negative 6x minus 8y, and then negative 25 times 2 is negative 50. Okay, so now we have our variables here that are going to eliminate when I add them. 6x plus negative 6x, that gives me 0. 15y minus 8y is 7y. And then 78 minus 50 is 28. So I divide both sides by 7. Same exact process that we've been doing this whole time. I get y equals 4. And now we're going to plug that back in. I'm going to plug that back in. Let's see, let me just erase this a little bit here so it's not so messy. I'm going to plug that back into the original here for the top equation. So 2x plus 5 times y, which we said is 4, and all of that equals 26. So I get 2x plus 20 equals 26. Go ahead and solve this like you normally would. And when I do all these steps, I get x equals 3. Okay, so my coordinate point would be 3, 4. Again, make sure that x coordinate is going before the y coordinate. And just to recap what we just did, the main difference here is we had to multiply both equations by a number, and I just took the smallest ones with the smallest constant in front of the variables, so the 2 and the 3, and simply multiply those together. So you multiply each equation by the opposite number. Okay, last slide here, we are going to do an application problem because this is really where systems of equations come in most handy, is when we're talking about real world problems. So Sam spent $23 to buy 12 flowers for his mom. Wow, Sam is a very kind son. Take notes, people. The bouquet contained roses and daisies. Each rose costs $2.50 and each daisy costs $1.50. How many of each type of flower did Sam buy? So as we look through this, we're given a couple different pieces of information. We're given information about the amount of money that Sam spent, so $23 total, each rose costing him $2.50 and each daisy costing him $1.50. And then we also are given the fact that he bought 12 roses, or 12 flowers, I should say, total, which comes from the combination of roses and daisies. Okay, so we need to know how many of each type of flower did he buy. Those are going to be our variables. So first, let's go ahead and define those. I'm just going to call them x and y just for consistency's sake. So let's call x the number of roses that he bought, and then we're going to let y be the number of daisies. So that's the first thing you want to do anytime you're approaching one of these word problems, is make sure you define what your variables are going to be. Okay, and then we're going to set up equations. Now, obviously, you guys can probably guess here, because we're dealing with systems of equations with two variables, we're probably going to have two equations here, and we already know we have two variables. So like I kind of color coordinated on here, we have information about the number of flowers and then the cost of the flowers. Okay, so the information about the number of flowers tells us that the amount of roses and daisies adds up to 12. So if we know the amount of roses is x, the amount of daisies is y, when we add those, we're going to get 12 as our total. Okay, so that covers the amount. Then our second equation is related to the amount of money that is spent. So we know the total is $23. How does he get that? $2.50 per rose, so 2.5 times the amount of roses, x, plus the cost of daisies, so 150 or 1.5 times each daisy, y, is going to give him that total of $23. Okay? So there are our two equations, and honestly, that typically is the hardest part of any application problem, is just setting up those equations. But again here, use deductive reasoning to think through, okay, I'm doing systems of equations. I know I'm probably going to have two equations. I'll have two variables here, so I should be given information for two different equations. Okay, so then I'm going to solve this like I normally would. I'm going to look to see, can I automatically eliminate a variable? Well, no, I have x and 2.5x, I have y and 1.5y. So I'm going to have to multiply by something here. Let's just say I want to get rid of my x's. So I have an x and a 2.5x. I would need my top equation to become a negative 2.5x to be the opposite of the bottom one. So that's what I'm going to multiply by here is a negative 2.5. And then I'm going to write this over to the side. So again, distribute here. So I get negative 2.5x plus, or just minus a negative 2.5y, because that becomes a minus sign, equals, and then believe it or not, 12 times negative 2.5 is actually a whole number, so negative 30, which is great. Okay, then we copy down our second equation. That is staying the same. And now we notice, okay, I can eliminate the x's because they're opposite signs. So going to go ahead and add these. So this gives me 0. Negative 2.5 plus 1.5 is negative 1. And then I just carry down the y. And then negative 30 plus 23 is negative 7. So to solve for y, I simply have to divide by this negative 1, and then I get y equals a positive 7, which should make sense in the context of the situation because we're talking about number of flowers, so you shouldn't end up with a negative number. That just wouldn't make sense. Okay, and then last step, we got to solve for the number of roses, x, so we plug this back in. I'm going to plug it in for this equation here just because I'm dealing with easier numbers, less decimals. So x plus the y value we found, which is 7, equals 12. And then we subtract 7, and we get 5. Okay, so now our coordinate point would be 5, 7. However, we are asked in the context of this situation to answer the question, how many of each type of flower did Sam buy? So we need to just write that as a statement saying he bought, X is representing roses again, so 5 of those, 5 roses. And then Y is representing daisies, so 7 daisies. And then we are done, okay? And make sure at the end, again, it should make sense in the context of the situation. 5 plus 7 still gives you the 12 if you wanted to plug these back in to the second equation to make sure that it does add up and multiply to give you 23 bucks that he spent. That's how you can confirm, and we do have both positive numbers or positive values because we're talking about number of flowers here. Okay, your homework for today is a 6.2 worksheet.